Good evening, ladies and gentlemen. I'm Roger Lanius. I'm the chair of the Space History Division here at the museum. Welcome to the third in a four-part series exploring space this year, where we're looking at the issues associated with global climate change and weather. We're pleased, and some of you I think were already here and you met Dr. Abdalati, and we're pleased to have him with us this evening. He is a scientist located at the Goddard Space Flight Center. He spent some time at the NASA headquarters before that time, where he runs the ICE science program. I think he's got a more formal term for that he will obviously talk to you a bit about this evening. Before we get to that presentation, I want to just say a little bit about the museum and the things that we're doing here, and just kind of give you an update on what's taking place at the National Air and Space Museum. Those of you who have been here lately know that we have a few new artifacts on display. Out in our Milestones of Flight gallery, we installed about 7 months ago now the Spaceship One spacecraft that went to the edge of space. It won the X Prize for flying twice in a 2-week period with people aboard. A very interesting and exciting object that's just outside in our Milestones of Flight gallery. We have underway, and you will see it in the next year or so, a new gallery that we're putting up called America by Air, dealing with the history of air transportation. All of us have flown on aircraft. All of us, I think, probably would agree it's not the most comfortable experience we've ever engaged in. That's not always been the case, and when you see this gallery, you will see how it has evolved over time. From a very luxurious approach to air transportation in the 1930s and 40s to where we are today with a form of mass transit with which we could not survive. And I think you will see that be opened about the summer of 2007. Stay tuned. It should be a lot of fun. If you have not done so, I would urge you to visit our Udvar Hazy Center, which is out near Dulles Airport. And it is a massive facility with a lot of very interesting and unique aircraft and spacecraft on display there. It includes an SR-71, it includes a Concorde supersonic transport, it includes the original Boeing 707 aircraft. It also includes the Space Shuttle Enterprise and a variety of other objects, large and small, and if you've not been there, please do treat yourself and go out. It's near the Dulles Airport, and it's open 7 days a week. And now, I think without further ado, I'd like to turn over the podium to Dr. Abdalati. He's going to speak to us this evening about, and the topic specifically is unraveling the mysteries of the Earth's changing ice cover. Please welcome Dr. Abdalati.
All right, well, thank you very much. I appreciate your time and attention, and I'm going to cover kind of a wide range of things related to the ice that should address sort of the layperson's interest for people without any expertise or experience or interest, for that matter, in ice, to some hopefully sufficiently sophisticated information that you may or may not know. I'd like to start with acknowledgments. First of all, NASA, partly for supporting this activity, but probably mostly for the job. It's good work if you can get it, and I've had lots of great experiences with them and their support of me over the years. Second, the National Air and Space Museum, obviously for the venue and the wonderful treatment throughout this evening. It's been great. Ball Aerospace, who's also contributing to this event, and also who built the first satellite mission specifically dedicated to measuring ice. So I'm especially grateful to Ball. The Polar Research Community, because it's largely their results. I'm going to show you some of my own in here, but I don't do it all. I like to tell people that, but the fact is I do very little of it. I talk about it a lot. And then other agencies, National Science Foundation, NOAA, and the DoD, because this is not something any one agency can really do. Understanding the Earth is hard work. It's complex, and it takes a lot of specialties, a lot of different foci to address the problem. And so our partners are particularly helpful in this. And finally, you. I really think it's critical to acknowledge the audience because the science is interesting to me. I love to do it, but it doesn't mean anything until it's communicated to people who can actually take the ideas forward, be responsible citizens, do something with the information. And I'm grateful for your time and attention in this venue, and I definitely want to acknowledge you. You're the only ones that got the exclamation point, but I'm excited about everybody. I should actually back up. Let me start, since this is the start of the lecture, I'll do this. If it were the end, I wouldn't. I'm going to ask you to close your eyes for just a minute. And think about, just keep it closed. I don't want to see anybody's eyes, just close them. Think about the coldest place you've ever been. Just the coldest, wherever it was. For some of you, that may be Pennsylvania. For others of you, it may be further north. Now think about that. Think about feeling cold. And then turn down the temperature about 10 degrees. And then turn up the wind about 20 miles an hour. And then turn down the temperature another 10 degrees and make it dark. And there are parts of the world that are like this for months at a time. And this is actually where I'm going to start, where I'm going to take you. And this is one of them. This is actually a picture from a flight I was on of the Antarctic Peninsula. So I'm going to talk to you about the cryosphere and the climate. The cryosphere refers to the ice-covered parts of the world. And it's got a number of elements. I'm only going to talk about the first three. Sea ice, which is just a thin veneer of frozen surface, ocean surface water. Ice sheets, which are these huge ice masses, Greenland and Antarctica. And the smaller glaciers and ice caps of the world. There's also lake and river ice, permafrost, snow. All of them are important for different reasons, but I'm not going to talk about all of them. So the ice cover of the world plays a critical function in the Earth system. It helps keep the planet cool. Did I tell you to open your eyes? I forgot, actually. I meant to do that, and I knew I'd forget. I practiced everything. You can open them if you haven't. It helps keep the planet cool. And the way it does this is by reflecting the sunlight that comes in. It's white, it's bright, sun shines on it, it does not get absorbed in the ocean. But ice has an interesting characteristic. As it starts to melt or it starts to retreat, it actually exposes the darker ocean water underneath. So when it's there, it reflects the energy. But as it retreats, the ocean starts to absorb the energy, which makes the oceans warm, which helps the ice to retreat, which exposes more ocean, which makes it warm and helps the ice retreat, and so on. This is called a positive feedback mechanism. It's a self-compounding effect. When it starts, it kind of wants to keep going. Now, fortunately, in this kind of scenario, winter comes every year. It has for a long time. It probably will in the future, which allows the ice to grow back and interrupt this process before it gets out of hand. So it's because of this process and a couple of others that the polar regions are actually predicted to warm more rapidly than the other parts of the world in the future. This is a particular climate model prediction. It's actually a little bit on the high end of the range of predictions for a particular future scenario. But they all say the same thing. They all say that the polar regions are going to get warmer than the rest of the world. And it's because of this sensitivity. This is just keep in mind, red is warm, yellow and whites are not warm. There's no cold on here in the future. Which actually brings me to another point that I should mention. As I go through this talk, I'd like to ask that you suspend any preconceptions you have about global warming, about global climate change. We'll come back to them later, okay? But as you're following what I'm talking about here, just let it go. Pay attention to the ice, how the ice works, and how it works in a changing climate. I'd rather, if you come in with a global change skepticism, you'll be like, oh, that's not true, that's not true. And if you're a firm believer, you'll be, of course it's true. Just think about what you're hearing, and then we'll come back to what it means in a broader context. So I talked about ice sheets, glaciers, and sea ice. The importance of sea ice in the climate system is really that it insulates the warm ocean water, keeps that, minimizes the interaction between the ocean and the atmosphere. and also reflects a lot of the incoming solar energy. So in this way, it affects atmosphere and ocean circulation quite significantly. Land ice, glaciers and ice sheets have a different importance. They're important to climate, but at NASA at least, why we focus on them is because of their potential contributions to sea level rise. And you'll see what this figure is here. This is Florida as it would look under a meter or 3-foot rise in sea level. Well, not really as it would look, because it wouldn't be red, but these parts would be gone. There it is, it's working. So in low-lying coastal areas, this is an obvious concern, but even in the high cliffs, it matters, because as the water laps against the sea, increased erosion occurs, and there's significant potential for damage. Now, the projections for the next 100 years, or out to the end of this century, range from about 9 to 90 centimeters of water. So about 3 feet of water at the upper end, which would result in this picture, to just about nothing, depending on how the ice sheets behave largely, but some other things. A rise in sea level is expensive, both in terms of life and safety, but also property. So for this reason, we study ice, for these two reasons. So how do you study ice? Well, one of the most enjoyable ways is to go there. This is the Petermann Glacier in northern Greenland. I went there a couple years ago. It's just spectacular, and someone asked why I went into this. When you're there and you're arriving and you see this, you can't imagine doing anything else. So you land, you set up your tents. This is what our camp looked like. There were five of us, I think, that year, and then a couple of work tents. And you may get home. This is the inside of my tent. And I'll be honest with you, if I'd known I'd been showing it in this forum, I probably would have tidied up a little bit. But I was walking by. I thought I'd take a picture. This is home. In graduate school, this was home for a few months at a time. Then I got married, and it couldn't be home for that long anymore. It became home for about a month at a time. And then we had my daughter, and it became home for about 2 weeks. And over time, I just shortened and shortened my visits. I finally understand the cycle. So you get a graduate student to stay a long time because they still think it's cool, and you get home to your family. It's a wonderful system. So we set up different kinds of equipment. This is a global positioning system receiver on the ice to measure how fast it's moving. Weather stations that we put out on different parts of Greenland to measure the various climate conditions. I'm only showing you a sampling. This is actually on a floating ice tongue, a floating chunk of ice at the end of a glacier. It's about 200 feet thick, and we drop these, well, you can see it, oceanographic equipment. I'll use the mouse to point to it. I think your battery's dead on the laser pointer. I think there was another one. Wow. Okay, I'll take my chances with this. Anyway, so you drop this instrument into the ocean water underneath to measure how it's melting from the underside. And in your spare, these aren't all the measurements by any means, it's just sampling, but in your spare time, sometimes the weather's good and you take in some sights. And sometimes the weather's bad and you take in no sights. You can't see anything, actually. But there's always something beautiful to see, and that's, again, part of the allure. But going to the field, as interesting as it is, has its challenges. And those challenges really are in the context of perspective, access, safety, and cost. And I think it's all summed up in this figure here. I mentioned graduate students. These are graduate students. And their advisor is in a boat with a very strong zoom, kind of far away, taking their picture. And their advisor was actually my PhD advisor, Connie Steffen. But I was fortunate enough to leave before he got funded for this project and left it to my successors. So we then go to the space-based perspective, and it's a whole other picture. I mean, I'll try and do this with the mouse, but that picture you saw is sort of a dot right about there. I don't know if you can see that. So how do you turn that picture into this? How do you translate the meaning of what you get in that location into this? Well, we use satellites. We use the view from space. And I want to stress that both are essential. You need to know what's happening at the surface to understand what you're seeing from this perspective, and vice versa. To understand the importance of what's going on at the surface, you need this kind of perspective. So satellites do all kinds of things. They go around the world every 100 minutes or so, at least most of the ones that I work with. They can see things that your eyes can't. And the nice thing is they don't get cold. They can, well, sometimes they do actually, but usually they don't. So we take this space-based perspective, and I'm going to now go into ice sheets, and a little tutorial on how ice sheets work, how they grow and shrink. Ice sheets grow when snow falls on them. It tends to fall in the middle. There it is. It tends to fall in the middle, higher altitude regions. And the edges, as it falls, the weight of the ice tends to push the ice out to the edges. It's kind of, a colleague of mine, Richard Alley, gives a wonderful analogy of really thick pancake batter. You know, as you pour it, it'll glop on in the middle and shove it outward at the edges. So at the edges of the ice sheet, they experience melting at the low-lying regions. The edges of the ice sheet also experience calving. Okay, icebergs break off, and there's also melting underneath the surface when the ice comes in contact with the ocean water. Now the interesting thing is, as climate warms, all of these processes increase. So not only do they melt more, but it snows more. So the growth mechanism increases. So there's this tension that influences sea level. So I'm going to start you in Antarctica and then go to Greenland. The Antarctic ice sheet, or ice sheets, there's a west and an east, are pretty remarkable in the sense that, first of all, they're at the bottom of the Earth, but the West Antarctic ice sheet, oh, I lose the laser, but the West Antarctic ice sheet in, well, here, the West Antarctic ice sheet, most of it is grounded or rests on a soft bed till, kind of like the muck you step in at the bottom of a swamp, below sea level. So if it starts to retreat, if the calving fronts of the glaciers that are flowing out the edges of the ice start to retreat, there's not really anything to stop them. And in fact, there's one particular area called the Pine Island Glacier, which is right here, referred to as the weak underbelly of the West Antarctic ice sheet. This is sort of the point of instability where a collapse could start. Now, some fun facts about Antarctica. It holds the equivalent of about 65 meters of sea level. If it were all to melt, and that many, many, many thousands of years away, so relax, oceans would go up actually about 60 meters because the Earth would deform under it, so it wouldn't quite go up the full 65. It experiences very little melt. It's well below freezing. The West Antarctic ice sheet has about 5 meters of sea level equivalent, and it's this instability which is what scientists are paying attention to, the weak underbelly. So we take satellite data, and I'll explain in a little bit how we go about getting this, but we take satellite data of the elevation changes. We can look at the flow rates of the ice sheets, how they're moving, and what we've been finding is East Antarctica, the region on the right side, has actually been growing. It's been snowing more than it's been discharging icebergs. This area is growing. The West Antarctic ice sheet in general is shrinking, in particular around that box, which, as I hope you recall from a minute ago, is the weak underbelly. And when you look at the figure on the right, this is a measure using sophisticated radar techniques that I won't explain now, but perhaps touch on later. We can look at the ice flow, and the purples are fast ice. Okay, ice that's really moving along about 1 kilometer a year. The blues and the greens are slower ice being drawn in by this fast ice. And those areas have been accelerating. And they've been accelerating because the floating ice tongues, the chunks out here, have been retreating as the ocean water's gotten warmer. And they've been moving back. Having trouble with the mouse. They've been moving back, and as they've been moving back, they sort of uncorked the ice, the glaciers that have fed them. There's a buttressing effect that's been removed allowing the glaciers to accelerate. Now I'm going to take you to the Antarctic Peninsula. It's important to point out most of Antarctica, the surface temperatures, have been cooling in the last couple of decades. Not warming, cooling. But the Antarctic Peninsula, shown in the red box in the figure on the left, has been warming by about 4 degrees in the last 50 years, faster than any place on Earth. And as it's been warming, it's been affecting the ice shelves. This is a floating ice shelf right here. This area is about the size of Delaware. For some reason, actually I said Delaware, I should have said Connecticut or something. For some reason, the unit of measure for ice is New England states. People talk about how big an iceberg is that broke off. But I want you to just look at this region in here. This is floating ice. It's about 10, 12,000 years old, hundreds and hundreds of feet thick. And in 1 week's time, I'm just taking you through, I'm sorry, 1 month's time, taking you through a progression. It just disappeared. 10,000 years of ice gone in a month. Now the interesting thing, in terms of sea level, it doesn't matter. It's been floating. It's already displaced the water it's going to displace. Melting floating ice doesn't raise sea level, at least not appreciatively. But the interesting thing is what's happened to the glaciers that have fed it. They've all sped up. Some by a factor of about 8. As you remove this buttressing effect, these glaciers are just flushing their ice out into the ocean, and they've been thinning remarkably. They've just been collapsing. Whereas the glaciers that feed the remnants of this ice shelf haven't changed in speed at all. Now this is particularly gratifying. It's unfortunate, but it's gratifying to some colleagues of mine who in the late 1970s theorized this. If you remove this barrier, the ice behind it is going to flush out. But in the 80s and 90s, there have been very sophisticated models that proved that wrong. But interestingly enough, in the early part of this decade, nature actually proved it right. So a little word of caution about the models we use. And I'm going to turn your attention to Greenland now. Oops. Now, most of Greenland actually experiences some level of melt in the summer. That's shown in red and pink here. I won't get into the different colors. Greenland's about, well, a little over 2 miles thick at its summit. It's very high. Antarctica is about 3 miles thick, or 3 miles high. The difference between Greenland and Antarctica, Greenland is much smaller. It's about 1/10 the size, but it melts a lot, and that water makes things slippery. And I'm going to explain that in a bit. This is some visible imagery, actually from the NOAA AVHRR instrument of the image of Greenland is from AVHRR. Actually, the image in the upper left is from the Aster sensor on the Terra platform that NASA launched. But this is a close-up of the glacier. Okay, this is called the Jakobshavn ice stream. And if you zoom in a little bit more, you can get sort of a sense of what these glaciers look like. You can see the main, I'll take my chances with this, the main glacier flowing here, the tributary flowing here. The ice front, you can see, the calving front, which I'll show you a picture of coming up, and crevasses. These are just big, big cracks in the ice and icebergs. And the crevasses are important because they enable us to track the flow of the ice from space. We watch these move over time, and you can figure out how fast the ice is moving. The calving front is important, too, because it's an important demarcation of what's happening at the ice front. This is where, literally, the ice meets the ocean. What you're looking at here is a calving front of the Jakobshavn ice stream. And this area here is about a football field high. At least it was in 1993. Right now it's about from the goalpost to the 5-yard line. It's true. You go back and you just can't see it. It was here 10 years ago. I don't know where it is now. And you can sort of see the cracks, the crevasses. If you look to the upper left, how it looks like it's ready to break off. This is the calving process. And over the years, this ice has calved very very steadily. Between 1850, which most say is kind of the end of the Little Ice Age, to about 1950, it's gone back a few kilometers every 20, 30 years, till it got to where it was in 1953, the rightmost yellow line up there. And it sat there for about 50 years for different reasons. Some of it, the geological structure. Some of it, maybe it finished responding to the last little ice age, which lasted about 400 years. But for whatever reason, it sat there for 50 years. And in 2000, it started kicking in again, retreating very rapidly, retreating more in 5 years than it actually did in any 60-year period prior to that. And when it did that, we tracked the movement of the crevasses, and it nearly doubled in its speed. This was one of the fastest glaciers in the world, and then it doubled its speed. So it goes about 5 feet an hour now, which for a glacier, that's hugely rapid. I don't think you'll fall over if you try and stand on it, but it's fast. You can watch it. And it also thinned. Again, the same phenomenon. It's flushing its ice out. As the ocean water is underneath it warm, the air temperatures above it warm, it starts to flush its ice out. Oh, thank you. Then I'm going to go back for just a second. I just wanted to point out this area here. This is sort of where the fissure starts, where the calving is going to begin. You can sort of see some of that up here, just enormous, enormous blocks of ice that you can kind of get a sense of the scale from this figure here, about 1 kilometer wide. So we've seen the calving front retreat in Jakobshavn, and guess what? It's happening elsewhere, particularly in southeastern Greenland. Glaciers, I said Jakobshavn used to be the fastest. It sped up. It was for sure the fastest, but other glaciers started getting a whole lot faster too. It's really cooking along the south, where the temperatures have been warmer. The north, it's a little questionable. We're seeing signs that suggest it might, but we don't know yet. Stay tuned. Maybe I'll come back next year and tell you what happened. Okay, if we look at the melt, and someone had asked me earlier about my graduate work. Actually, one of the things I did was figure out a way to use microwaves to track the melt in Greenland. And this, Connie Steffen was my advisor. This is a plot of the melt characteristics over the last 26 years where we've had the satellite data to look at this. 31% increase. Now, I got to tell you, 26 years is a short period of time in a climatological sense. So I'm not going to say this spells the end of the world, but some interesting things happen, regardless of whether this is a part of a huge, long, horrible trend or whether it's just a blip in an annual cycle. I do think it's part of a longer trend myself. When ice melts or snow melts at the surface, it collects in these ponds. These are melt ponds, and they're anywhere from 100 feet to a couple miles wide, from 3 feet to 50 feet deep, depending on where you are. They're all over the melt zone of the Greenland ice sheet, the low-lying areas. And what happens to this water? Some of it just runs off into the ocean. But more significantly, some of it finds its way to the bottom, and it does it in 2 ways. There are under subsurface tunnels called moulins that when the lakes build up enough, they build up enough pressure, they force these things open, and the water flows through these big holes. These are people that I'm glad I'm not one of them, standing near the edge. Very seasoned glaciologists, though. One of them, I think, is Mark Meyer from the University of Colorado. Another way it does is through crevasses, just these cracks in the ice. These crevasses fill with water, and the weight of the water pries open the crevasse, making it bigger. More water runs in, it weighs more, it pries it open further, and so on and so on. And so the water can actually go through a mile thick of ice and cause it to accelerate. So melt is significant not just because of the runoff, but because of the impact on the dynamics, the impact of the flow. And I think that's part of what we're seeing in the last picture that I showed you. I'm going to take you to some of the glaciers and smaller ice caps. The Greenland and Antarctic ice sheets are huge. They're hundreds and hundreds of miles wide, thousands if you look at the longer dimension, or 1,000 maybe, if you look at the longer dimension. These ice caps are typically 80 miles, the bigger ones 80 miles wide, maybe 60 miles wide. Glaciers are much smaller and narrower. But these small ice masses actually have a quick response to climate. They're closer to melting point. They're smaller. They can respond very rapidly. And it turns out that some of the biggest sea level contributions are coming from the melting glaciers in Alaska. I should point out, though, that this mechanism and the breakup of the ice shelves that'll remove the buttressing effect and cause the ice to flow faster. Sorry, I think I just pointed at someone. Sort of shatter the myth that ice sheets respond very slowly to climate change. It's true. If you raise the surface temperature of an ice sheet 5 degrees, it'll take 1,000 years for the bottom of the ice to feel anything, probably more, actually. But if you raise the ocean temperature a little bit, it starts to chip away at the edges and allow the ice to flush out. Glaciers respond fairly quickly, but by different mechanisms. And this is a sampling of glaciers all over the world of their retreat characteristics, which is analogous to their size. The only thing I want you to notice is that nearly all of them, nearly all the glaciers are shrinking. They're actually disappearing. That means the melt is greater than the snowfall, or the calving and melt combined are greater than the snowfall. But it's hard to measure this stuff on glaciers. There are something like 160,000 named glaciers in the world, another 50 without names. I'd like to get one named after me, but I'll have to discover something. There's enough for everybody in case you're interested. But anyway, a couple 100,000 glaciers. So it's hard to measure them all. But with satellites, we're actually taking snapshots all over the world of their footprints and their behavior. And one way we're doing it, when people think of satellite images, you think of a picture, okay, a snapshot, which is one very effective use or capability of satellites. But there are others. There are other ways of looking at these things. And one particularly fascinating mission that we launched a few years back is called the GRACE mission, Gravity Recovery and Climate Experiment. And here's your quick lesson in a few interesting methods of remote sensing. GRACE, rather than looking at the surface below, actually looks at the distance between two satellites. And the orbital mechanics of, the mechanics of satellite motion are such that the speed that a satellite orbits the Earth is directly related to the mass of what's beneath it. So when a satellite is flying along, if you imagine this as a big lump of ice, two satellites are flying along. The first one flies over this big mass. It accelerates. The second one hasn't because it hasn't gotten there yet. So there's some increased distance between the two. Then they fly. The second one catches it. It accelerates, and they go back to the spacing that they had over here. And the amount of distance between the two satellites tells us how much mass is at that ice sheet or at that glacier. We do this very precisely with GRACE. By measuring the distance between the satellites, we can figure out the mass underneath the satellites. By measuring how that distance changes over time, we can figure out how much the ice mass has changed over time, and subsequently its contribution to sea level. So here is just a map of the western coast of North America, Baja California, Alaska. And the Alaskan glaciers and the glaciers in the Canadian Rockies all shrinking quite a bit. This is millimeters of year is actually millimeters of water a year. And if you spread that out, that's just a surface elevation change scaled back to water. If you spread that out over all of the Alaskan glaciers, it becomes enormous. There's another mission called the Ice Cloud and Land Elevation Satellite. And this is a personal favorite of mine because I was heavily involved with it for a lot of years. This was launched in January 2003, and it's the first mission. This was designed by the satellite itself. The spacecraft was designed and built by Ball Aerospace, the instrument at NASA Goddard, by people in my group. This is the first mission designed specifically for polar, for ice applications. It does a lot of other things, but specifically for ice. And it's the only one flying. The Europeans had another mission, but there was an unfortunate problem at launch. So IceSat is kind of it for space-based, for ice-based measurements. And the way it works is it fires a laser at the surface of the Earth. We measure the travel time of the laser pulse from the satellite to the surface and back. And from that, we get the range from the satellite to the surface, because light travels at a constant speed. When we couple that with precise information from GPS about the position of the satellite, we can measure the elevation of the surface. Very, very accurate. Each laser pulse is about 15 centimeters. When we aggregate a bunch of them, we can actually detect changes about about a centimeter, less than half an inch. So the ICESat mission, we fly this pole to pole over and over, and you start to lay down a bunch of ground tracks that look like this. The red shows the surface of the ice cover. This stuff up here actually shows the intervening clouds and aerosols in the atmosphere. So we get both atmospheric information but also surface information, and over time we get elevation change information. A very, very powerful capability, but wait, there's more. We actually have lots of satellites up there that look at lots of different pieces of the Earth system puzzle. I showed two that have specific utility to ice, but we have close to 20 with maybe 80+ instruments on them that measure different components of the Earth system so that we can put all this information into a better picture of the Earth as a whole. I'm going to move to sea ice now. Okay, that's it for land ice. This animation or visualization shows the annual cycle of sea ice. In the winter, it grows to the edges. In the summer, it retreats to some seasonal minimum of what we call perennial ice, this area right here. And then it grows again and contracts, does this year after year after year. Now, if we look at the ice characteristics over time, again, it's the microwave satellite data. So we've only had this data since about the late 1978. It tells us that the sea ice has been shrinking at about 3% a year. But if we look at the perennial ice cover, this is now year to year of what's left at the end of the summer. Okay, we see a trend from the early part of the record to the late part of the record. I've averaged 4 years in each so that I couldn't be accused of just, cherry picking things that make my point. The bottom line is the sea ice cover is shrinking. There's a lot of variability to that, but it's shrinking, and it's shrinking at about 10% per decade. The yellow line is the average, sort of the last 25 years. The white shows where the ice was at the end of 2005. And I'll tell you this, 2006 promises to shrink this even further. We can already tell that in April. If you couple this shrinking in area, this is particularly important. This is the ice with staying power. This is the ice that survives the melt season year after year. So it's the thick, hardy stuff. So even when it grows back, if it grows back thinner and weaker and more vulnerable until it can stick around for a while if the climate conditions are such that it does. So this is important, what's happening to the perennial ice cover, because it's a little different than the seasonal stuff. Now, submarine data for the last few decades is individual sampling, so there are certain sampling issues associated with it, but they suggest that the thickness has diminished by about 40% in the last couple decades. So shrinking in area, shrinking in thickness. And some predictions are for an ice-free Arctic in the summer in as little as 50 years. There's actually one guy who says 20 years. We'll know in 20 years, I guess. Others say 100 years. A few say never. The estimates vary, but 50 to 100 years is sort of the accepted range of likelihood. So thickness, the rate at which this diminishes depends on how thick it is, and we can't really see that from overhead. So it's always been a challenge or an interest to be able to measure thickness from space. Well, there's a way we can do that, and we can do that with ICESat. And we can do it because the freeboard height, the amount of ice that floats above water, is directly proportional, as a function of their relative densities, to the thickness of the ice itself. So with satellites, and in particular ICESat, we fire a laser, we can measure the surface. There are tools, radar or microwave combined with lasers, that let us figure out how much snow is on the surface. So we can get the freeboard height, the height above the ocean. In this figure, this is ocean water. This is the surface of the water. This is a slab of ice. This is snow. We can combine all that information and estimate the thickness of the ice just by measuring how high it extends above the water. And this is just an example of that. This is a radar image that shows an IceSat satellite ground track over open water, which if you go back to the other figure, open water is here, ice is here. And you see the top of this line is essentially that freeboard height measurement. The bottom, or this range, is the thickness of the ice. And you can see it reaches 0 where we don't have any ice. It's sort of a sanity check. It's kind of a no-brainer. But in this way, we can start to measure the ice thickness. Now, we only have 3 years of data, actually 4 now, but the 4th haven't been processed yet. But they're telling us interesting things about the behavior of the ice. This area here, this is just wintertime ice cover. We see a big pileup of ice in 2005, whether that's just growing faster or the winds are blowing the ice over and piling it up on the shore, we don't know. We'll know in time. We can learn this from other data, but these are relatively new and have not been thoroughly analyzed. This is an area that seems to, over the last 25 years, become vulnerable and opened up and had a limited refreeze in the wintertime. And so we combine this information with the other to get a much more comprehensive picture of what the ice is doing. You can't give a talk about the polar regions without showing polar bears. So here's my obligatory, aren't they cute, polar bear picture. I mentioned the ice-free Arctic in the summer. Well, there's significant implications of that, some favorable, some unfavorable. We get rid of the ice, there's more heat absorbed by the Earth's surface, by the ocean water. And actually, when that happens, more water vapor enters the atmosphere, and water vapor is actually a pretty powerful greenhouse gas. There's the potential for new climate patterns. If you get rid of the ice, the atmospheric circulation, the ocean circulation might change significantly. And also change in wildlife habitat. As the distance between ice flows grows and grows, it gets harder and harder for the polar bears to find their food and swim those distances. It's great if you're a seal, but it's bad if you're a polar bear. Nobody ever shows pictures of seals, so I guess they get top billing. But you also need to think about the implications of an ice-free Arctic from a societal standpoint. This is the current shipping route from Asia to Western Europe through the Suez Canal and up and around. In an ice-free Arctic, it becomes much shorter. And this distance has significant economic implications. The potential for affecting the trade balance, who knows? I certainly don't, but I got to believe it's there. Improved access to resources. There are resources at the bottom of the Arctic Ocean. There's probably oil there, among other things. So if logistically we don't have to contend with ice part of the year, it's easier to access the resources. There are security issues. What happens if you can access Canada, Alaska from a northerly route? Believe me, the military has paid a lot of attention to this scenario. Other recent changes, just sort of a hit list of Arctic change, largely Arctic changes, but it's also high latitudes in general. The Arctic is warming about twice as fast as the rest of the world. The Antarctic Peninsula is warming more than any place else in the world. But most of the Antarctic surface has actually been cooling. That's important. The air temperatures in winter have been going up, but the surface temperatures have really been cooling. Melting permafrost, I didn't talk about that, but it's permanently frozen soil. When that melts, structures that rest on that soil start to collapse. And it turns out that the state of Alaska spends, I think it's like 1.5% of its state budget on infrastructure repairs related to permafrost melting. Earlier melt onset of Arctic sea ice, not Antarctic, depends on where you look, but Arctic. Earlier lake and river ice breakup, earlier snowmelt in the northern hemisphere, and some indication of changes in atmospheric and ocean circulation. Now, in the last few minutes, I'm going to take you to a little bit different place. I'm going to take you inside the ice. You've all heard about ice cores. And ice cores are phenomenal. They're a wonderful tool because They trap information about past climates. They trap air from past climates, and they trap chemical structure from past climates, which tells us what the temperatures might have been. Huge amount of information about the history and for a temporal context of the kinds of changes we're seeing are stored in the ice cores. Now, I want you to think about this. This is actually, I got this from Richard Alley, who authored a report, who led a report on abrupt climate change. Just look at this green curve. This is temperature derived from an ice core in Greenland for the last about 10,000 years. We see some wiggles, little ups and downs here. What's important to note, though, is that if you look at this peak, I should tell you this is the present, this is time backwards. So you got to think in that context. 5, 10, 15,000 years ago. So we're here. We're actually about there. If you look at this little peak here, this is when the Vikings settled Greenland. And it actually was green at the southern tip where they landed, kind of a mossy green, but it was green. It wasn't a big hoax like a lot of people say. Got to keep people out of Greenland. I don't know why anyone would think that. But so this is when they settled Greenland. Now this drop of a couple of degrees is when they disappeared from Greenland. They couldn't handle it. They died or they left. People didn't stay. Okay? If we look a little further back, this is what's been in our past. And forget your SUVs and coal and all of that stuff. This is what happened before without any of that stuff. Big, big, big changes in short periods of time. Now, if we look back 400,000 years, this is from the ice core in Vostok in Antarctica, we see temperature, this is carbon dioxide and temperature, and it goes through cycles. The Earth goes through natural cycles that are directly related to its orientation and proximity to the sun, among a couple of other things. So there's about a 100,000 year cycle, there's about a 44,000 year cycle, and about a 20,000, 23,000 year cycle. So this is where we've been, in a carbon dioxide sense and in a temperature sense. And this is where we are now in terms of carbon dioxide in the atmosphere. This is projections for the future in a CO2 carbon dioxide doubling scenario. And I'm not saying it's going to double, I'm saying that's one of the scenarios. Could stay the same, it's probably not going to go down, could go up a little, but this gives you a real 400,000 year context of where we are. And it starts to make us wonder if what we know and believe about the climate still applies in that scenario. We don't know, because we haven't been there. Even our models of what's happening today are hard to nail, much less what happened before. So here's your little tutorial on climate stability. I tried to make the circles big and easy to follow. But basically, there are two kinds of systems in the world. There are actually more, but for the purposes of this discussion, there are stable systems and unstable systems. Stable systems are systems that, when perturbed, will return to their normal state. You imagine a marble in a bowl, you shove it up to the edge of the bowl a little, you let go, it rolls around, and it comes right back there. That's a stable system. Negative feedbacks, feedbacks that correct themselves. This is an unstable system, positive feedbacks. You flip your bowl over, put the marble on the top, nudge it a little, it'll roll down the hill. Okay? We've been in a fairly stable climate system for the last 10,000 years or so. But what happens if you nudge it to some tipping point, as they like to call it? You cross the threshold of stability into some new system. Okay, so you perturb this is a metaphor for the climate. You perturb it, you perturb it, you perturb it, and all of a sudden you're in some new state. It takes a lot to come back to this state. Well, this is sort of what the thinking is with regard to abrupt climate change, or tipping points, if you've heard that. You can push, 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 and potentially enter a new state. Are we doing that? I don't know. But there's evidence that it's happened in the past. And again, if you suspend your human contributions for the timing, just think of the Earth as a system that works in a certain way. It's in our past, and it's likely in our future. Now, what does this mean? And I'm almost done here. Well, a lot of the ocean circulation in the Atlantic is driven actually by the cold, salty waters up near the poles. They're cold, they're dense, because as sea ice freezes, it rejects salt into the ocean water, so they sink, and they draw up warm water from the lower latitudes. This is all part of the global conveyor belt of ocean circulation. This has been around for a while. This is roughly a description of how ocean circulation works on the planet. Well, what happens, I'm not sure, what happens if you disturb that? Okay, if all of a sudden you melt Greenland a lot, you stop forming sea ice, you put all this fresh water into the system, into the system here, all of a sudden maybe you suppress that sinking. Well, what does that do? Well, that stops drawing up heat from the lower, like the Gulf Stream, from the lower latitudes to warm the higher latitudes. We don't know. You know, you remove the ice boundary at the bottom, what does that do to atmospheric circulation? There are theories, and it's a subject of study, but the potential is really quite significant. So to summarize what I've covered, essentially, I'm going to go back to the space-based observations. They provide a critical perspective and context for understanding changes in the ice cover. It is essential to go to the ice and see what's happening, but for context and perspective, you really need that view. So we combine this with field observations and models and get a better picture of what's going on. Glaciers and ice sheets are contributing to sea level rise. Now, large parts of the ice sheets are growing, which actually lowers sea level. But more significant or larger parts are actually shrinking, so the net effect is an increase in sea level. Glaciers and ice sheets, in particular ice sheets, respond rapidly to climate. It isn't centuries to millennia process anymore. It's a months to years to decades process. What happens today matters. Sea ice is declining in the Arctic. I didn't talk much about the Antarctic, but it's not doing much down there. And there are reasons which, if I had more time, I would go into. But the impacts of these changes could be large. And because of the significance, and because of the recognized significance of the polar regions, not just because of what they're doing now, 2007-2008 marks what's called the International Polar Year, which is a coordinated international effort to study the polar regions and their role and function in the Earth system. So I want to leave you with a couple of thoughts. Climatologically, we're in unfamiliar territory, or we're approaching unfamiliar territory. People haven't really been here before. And we're seeing the ice cover of the world respond quite substantially. We're seeing big changes in some areas, not so big changes in others, but some things are big. And the effectiveness of society's response to those changes is going to depend on three things. It's going to depend on how big the changes are. It's going to depend on how fast they occur. And it's going to depend on our ability to see it coming. Okay, the smaller the first two are and the larger the third is, or the smaller the changes, the slower they happen, and the better our ability to predict them, we can adapt, mitigate, capitalize even in some cases on those changes. But if they're big and fast and we don't see them coming, there's going to be a problem. So back to NASA, back to satellites. We start up close, take that information, zoom out, take in the ice sheet as a whole, take in the sea ice as a whole, take in the northern hemisphere as a whole, take in the Earth as a whole, and we start to get a much better picture, a much clearer understanding of what's going on and how that impacts us. And finally, thank you. I come back to how I started. Thanks to you for your attention and care.
Thank you so much. Would you entertain some questions?
Gladly, for as long as you want. Probably longer, actually.
Up here.
That's a good question. The question was, since water expands as it freezes, why would the water rise as it melts? And it's the difference of whether the ice is floating in the water or whether it's sitting on land and spilling into the water. What you said is exactly right. It's like your ice cube in a glass of water. You put it in, you watch the water level, the ice cube melts, it never changes. Because once you put it in, it displaces the water. But what I'm talking about, when ice sheets break into the ocean, calve into the ocean, that's like putting the ice cube in the glass. And when you do that, the water raises in the glass.
Yes, sir.
All the ice melted theoretically at sea level plus what might have been the sea level with the last major ice?
15,000 years ago, the sea level was 125 meters lower than it is today. And that was when, so that's close to 400 feet. That was when the Laurentide ice sheet covered most of North America down to about Pennsylvania and Wisconsin. And what I didn't say, I think it was up there, but I didn't say it, is when those started to retreat. Sea level is currently going up. In the last 100 years, sea level's gone up about a little less than 2 millimeters a year, about the thickness of a nickel. In the last 10 years, it's gone up 3 millimeters a year, about the thickness of a nickel and a dime, if you're keeping track. That's not to say it's getting faster. We don't know. 10 years is a short period of time, if that's part of an ongoing trend or just part of the oscillation. But there have been times when the Laurentide ice sheet collapsed that sea level went up about 3 feet in 20 years. And you go back to that map of Florida that I showed. If you can imagine Florida reaching that state in 20 years, well, some people might be happy, but most people wouldn't be. The people inland would probably be happy.
Yes, sir.
When you had your pictures that were generated by the ice over Alaska, showing how they came down, there was a red area called
Yeah.
over the illusion. What was come up?
That is a couple things. I'm not sure I can get back to it too quickly, so I'll just keep talking until I get there. On land, that's actually probably precipitation. In the oceans, there's actually the movement of denser ocean water or water masses that change the weight of the ocean under the satellite. I'm getting there. Sorry, it's a long, slow. Oh, I'm sorry. The question was, and I'm trying to get to the figure, in the case, oh, I went past it. The case of Alaska, I showed the GRACE data that showed this big bullseye of lost mass in Alaska. And the question was, what was the red stuff, the gained mass elsewhere? Sorry, I don't know why I'm having such a problem. Let me focus on this and get to it. Was it the one I just passed? You're talking about the sea ice? You're talking about Alaska. Yeah, I'm sorry, it's coming up. I think it's here. It's thinking, that's the problem. Anyway, where we lose mass in one area, actually the Earth uplifts in other places, the mass changes, but it also may snow more in these other places. Boy, I don't even remember my own presentation. It may snow more in these other places, and ocean water, dense ocean water, moves to different parts of the ocean. It's pretty precise. It can detect significantly small changes in mass.
Yes, sir.
Is this melting messing up the field work? It's melting the evolution that scientists select?
You know, that's a great question. The question was, is this melting messing up the field work? There is a guy by the name of Lonnie Thompson at The Ohio State University who is the undisputed world leader in temperate climate ice core retrievals with the past record. And Lonnie has been pleading for support to grab the ice while it's still there because the record is disappearing. In Greenland and Antarctica, we don't have to worry about it for a good long time. I will say it's messing up my field work. You hate to be wet when there's nothing worse. It's fine to be cold, but wet is awful. So in a logistical sense, it becomes more complicated. But in terms of the record, it's certainly a problem with the tropical glaciers. Not quite as much, although it does do some contamination in Greenland, and really no problem in Antarctica. Well, correlation in what sense? The question was, is there any correlation with other planets like Mars on these ice caps? Are you asking if we can relate the behavior of one to another? The answer to that is absolutely. We actually have learned a lot about the Martian ice caps, North and South Pole, based on what we've seen in Greenland and Antarctica. Their flow, their behavior, some of the characteristics. Haven't learned so much in the other direction because we've got a lot more information about those on our Earth. But there are certain features in the Martian ice cap that we can relate to what we see, on the Earth as well. Pardon? Not really, because the Martian ice cap is not so dominated. It's not melting. It doesn't experience quite the same processes. It's not flowing into an ocean. The Martian ice cap sits on land and actually extends beneath the land cover. So the factors that affect the edges of the ice sheets on Earth are the melting and the interaction with the ocean, and neither of those are really occurring.
Let's take one final question. Yes, young man up here.
What did I want to be when I was a kid? Probably the most persistent thing I wanted to be was an astronaut, and I got partway there in the sense that I came to NASA. But I think your interest. I used to want to be all kinds of things, and I never would have thought I'd be this, but I'm glad I did. And the great thing about being a kid is it's all in front of you. So think about being whatever you want, and you'll probably get to someplace good.
That's a good place to end. Our speaker will be happy to stick around down here for a little while afterwards, and you're welcome to talk to him at your leisure. Before we close, I would just like to remind you, mark your calendars, on June 6th, we'll have the last of our Exploring Space lectures for this particular year. The speaker that night will be James Fleming from Colby College. His topic is Exploring Weather and Climate in History, a history of cutting edges and killer apps. So it ought to be great. We hope to see all of you here on the 6th of June to hear that last and final presentation in this series for this year. Thank you all for coming. Let's thank Dr. Abdalati one more time.